morning. It's wonderful to be here. It's truly an honor for me to be on this stage, and frankly, a tough act to follow to be after Dr. Prentice. So I could listen to him all day, that's for sure. But it's also an honor for me to represent the men and women of the Air Force Research Laboratory. I'm going to tell you a little about who they are, what they do, why we are interested in quantum information science, quantum technologies, and kind of a little bit about how we approach our scientific portfolio. And our men and women, we have about 10,000 of them. They're located throughout the United States as well as around the world, including Australia, Brazil, Chile, Japan, and Europe. And we do this because we are always looking to take risks, to solve problems for the Air Force and the Space Force, and to accelerate technologies to the field to ensure our national security. And so it's really an honor to be here and tell you a little bit more about why and how we do our business. So to begin with, we've been in this business for quite some time. In fact, the research laboratory has been around for well over 100 years. We know that as a result of World War I, that the military was using outdated equipment. We were reliant on European aerospace technologies. And it was decided that we really need to invest in our own indigenous capabilities so that we can stay at the cutting edge of what technology offers. And of course, by the time World War II rolled around, we had a really solid scientific approach. Hope this isn't coming off yet. And we were able to partner with industry and academia on a number of aerospace technologies. And in fact, we established an independent board of advisors called the Scientific Advisory Board, which still exists to this day. And their whole role is to ensure that we are connected with technologies that are coming online, technologies like quantum, like artificial intelligence and biotech, just to name a few, and to guide us and ensure that we are connected to some of the most exciting opportunities that are out there, and then how can we apply them for the purposes that we have in the military. So, of course, quantum falls into this category. The collection, generation, processing, and communication of information, again, is an area that we've been involved in for quite some time. If you've heard anything about the internet or global positioning satellite, these are some information technologies that the military, the Air Force Research Lab, has contributed to in the past, in fact. And so quantum is no different. Of course, what we are looking for is information to be resilient, to be reliable, accurate, and secure. And of course, we're trying to do that with today's technologies, but also applying it to quantum technologies. So when we look at quantum more specifically, we really take a long view toward how we're going to build our capabilities, build our knowledge in this area. And so for a long time, we have been invested in some related technologies. If you're familiar with lasers, laser cooling, and trapped ions, these are technologies that the lab has invested in. And the other thing that you really need to know about the research lab is we are not in the business of manufacturing or selling technologies. We are very interested in science and technology, ensuring that, kind of to the question from the last presentation, that there's a solid understanding of what is real and what is myth. And we like serving the role of honest brokers and advising our leaders in government, in the Air Force and the Space Force on what the true potential of this particular technology, but also others may be. But as I mentioned, we're not in the business of manufacturing, and so we see that one of the best advantages that we can have is partnering with companies, partnering with academia, so that you can further mature the technologies and deliver it to the field faster, whether it is for commercial or military applications. And for example, with that laser cooling technology that we've been interested in, and actually that's been around since the 1950s, one of the things we have been able to do recently is we transferred what we had grown in the lab for laser cooling. We partnered with a small business who is here this week, in fact, and that small business took the technology and they matured it so that it could cool atoms to 1/1,000,000th of a degree of absolute zero. And they are working to fly this trapped ion on the International Space Station. And so it turns out it's a real win-win symbiotic relationship between the government, between industry and academia, and it enables these technologies to really accelerate, and everyone gets to use their, the expertise that they have and what you can bring in order to develop this technology further. So in kind of looking at the ecosystem of the Air Force and the Space Force, you see a picture here of the kinds of environments that we are flying in, that we're operating in, whether it's in air or space. And as you can see, sharing this information across multiple domains in very austere environments over really long distances, there is the potential where quantum can help us do this better. And as I mentioned, we're really interested in resilient, in reliable, accurate, and secure information. And we're taking an approach with quantum that is fairly broad. We're not just looking at one application, but looking at multiple. And you can kind of see the jigsaw puzzle up there in the top left. So we're looking at timing and sensing, networking and computing, as well as the supply chain and workforce development. So in terms of timing, what we are looking at there is atomic clocks, and we have a number of folks that are working on this technology to make it more accurate, but also to make it smaller and more portable for some of the systems that you see there. And in fact, one of the things that the team has told me about recently is they're looking to build these new types of atomic clocks and fly them on satellites. We're looking to I'll get to the other example in a minute, but looking to get these atomic clocks in both in space and on air systems so that we get the timing right and our folks know where they are at the appropriate time that they should be. In terms of sensing as well, we are looking at a number of quantum capabilities. If GPS, for example, becomes unavailable, then what kinds of resilient or redundant systems can we rely on? Inertial navigation and leveraging quantum technologies for sensing. And again, that lower size, weight, and power constraints are of particular importance to us. And I think kind of to compare what we're looking at the research lab compared to what Dr. Prentice was talking about a little bit earlier, we are really looking at the applications of it and trying to see how can we make quantum a more practical application for our purposes, but also commercial ones as well. On the networking side, we are looking at heterogeneous approaches for nodes, for example. The team is looking at everything from having nodes performing different functions, whether it's processing or sensing, and how can we best capitalize on the diversity of technologies that are out there. The team is looking at everything from trapped ion technologies to superconducting, and of course, photonic integrated circuits. So all those together, and how can we best lay the foundation for the networking of the future that may be helpful in this type of scenario across these great distances that we're operating in. On the computing side, one of the myths might be that a research lab is trying to build a quantum computer, and I'll dispel that right now. No, we're not. One of the things we are partnering is to understand what is going out there in the world in terms of quantum computing. We're partnering with folks. We're watching and leveraging some of those technologies. We are looking at some of the algorithm developments that are ongoing. We are looking at that in-house. But also, are there any devices that are being developed in the commercial world? And if industry is interested in sharing that with us, could we better understand what those capabilities are? And so that's the basic approach that we're taking with computing, and it's to help seed the industry and ensure that you are successful in maturing these technologies. Of course, none of these applications would be successful if you don't have a reliable supply chain of technologies and the supporting infrastructure surrounding it. And so ensuring that is part of how we're approaching the technology development is one of the key points of emphasis for the research lab. There's a lot of non-recurring engineering, a lot of expensive equipment, and so it's a very costly endeavor. And so how do we partner with industry? Can we contract out, for example, in some technologies and do others in-house, and finding the best affordable mix of that? So taking a holistic look at the supply chain and all the enabling technologies, whether it's refrigeration and cooling and the lasers that we were talking about earlier. It's all part that we are ensuring that it's a robust pipeline. On the workforce development, this is potentially the most important role that the laboratory has. And I was talking with my team earlier and learning about some of the efforts that they have in workforce development. Of course, you don't become a quantum physicist overnight, but we also know that it's not just physics that is needed to realize the potential of quantum. We need to leverage electronics. We need to leverage computer science, computer engineering, and a whole host of technologies. And we want undergrads and graduates to understand that you don't have to necessarily only be the next John Prentice to be involved in this exciting new technology development, that there is a role for the broader community to benefit, to learn from. And so we're really trying to get the word out there, and again, make sure that there is a distinction between what is the reality of quantum and what is the myth. So this is a slide that I borrowed from our DoD partners, Dr. John Burke, and he created this scale to look at what is the potential military impact of a number of quantum technologies versus the readiness of that technology to be used in field conditions, for example. So in terms of military impact, that's on the y-axis. You can see up there in the top left, a full-scale quantum computer would have a high military impact, but as this audience knows, that's quite some time away from being ready to be fielded. This is an area where we would want to leverage and partner and watch development in academia and try to encourage the continued development of this technology. Over there on the far right, in terms of military readiness, but also high on the military impact, you see GPS atomic clocks. Something where it is more mature. We see it as a viable technology that we can start to leverage today. We do need to focus on getting those clocks more portable, more affordable, and smaller in scale. But lower toward the bottom of the y-axis and the left of the x-axis, quantum networking concepts. You see there's a big orange circle there. It might be hard to read when you're in the back of the room, but ultimately it suggests there's a lot of uncertainty in this area, a lot of work to be done, and a lot of work to be done to bring this technology to bear. And of course, this is where we're partnering and trying to ensure that we are building the foundation of something that is usable by multiple communities. And I think I mentioned already the heterogeneous nature of what we want to see the quantum networking concepts to proceed. So this is just kind of a good picture of the relative technologies that we are invested in, that we're partnering in, and how we see them coming to bear and on what timelines, right? So not everything is going to be ready tomorrow, but we're just trying to be prepared and ensuring the right foundation. So the last thing that I really want to talk about is how are we building these partnerships with industry and across the government as well as with academia. We have a number of tools that we're using. We have a large number of activities that are going on. Of course, one thing I'll point you to if you're here in the room is to go see the booth and the experts that we've brought, and I'd encourage you to go talk to them and have them help answer some of your questions. But I'll point to the two in the bottom center of this chart here. So on the small business innovation and technology transfer, the great news about being in an exciting technology area like quantum is there are some new entrants to the field, industry popping up that want to see this technology go further. And we in the lab are really trying to encourage those businesses to be successful. And we're doing that in a variety of ways: small business innovative research, small business technology transfer, like the laser cooling technology I spoke about earlier. In 2020, for example, we hosted, specific to quantum, we hosted 2 quantum colliders, and they were very successful. In June of 2020, for example, we had about $5 million that was awarded to, I can't remember the number of companies. I kind of want to say about 35 small businesses that were involved and got some research contracts to mature technologies that they were working on. And then later that same year, in December of 2020, we had a second quantum collider where these phase 1 SIBRs matured into phase 2s, which is basically a higher dollar value, and we awarded over $35 million in contracts. That's really exciting, and it's really helpful to get a small business to get their feet off the ground and to get further down the road in advancing their technologies. And so we're really excited about opportunities like that. But also on the university side, you see multidisciplinary university research initiatives. And ultimately, these MURIs allow universities from a variety of locations to take a multidisciplinary approach. We award a couple $1 million for these types of efforts so that they can collectively start to solve some challenges in whatever technology area it is. And of course, quantum, there are a number of MURIs that we have out there looking at some of the next generation of quantum technologies. So I'm about out of time, but I just really want to say thank you for allowing me to be here and tell you a little about the research lab, our interests, both on the Air Force side, the Space Force side, and how we want to partner with academia and industry so that you're successful, so that the science and technology is rigorous, and that we can advance those technologies for a whole host of reasons.